So hello and welcome back. So in this video we want to talk about validating statements. So let's go through the text. Let's see what we have. It says in this section we will discuss when a statement is true. So far we have been learning different things about basically doing different sorts of operations like negation. Basically so far we had the negation of a statement. Basically we had the negation of a statement. We had writing the statement in the if-then form. We had the contrapositive of a statement. And we had the converse of a statement. Moreover, we also talked a little bit about the connectives, and we talked about the connective or, we talked about quantifiers. Basically, for every and for basically there exists, for example, and that's I suppose everything that we have talked about so far. We talked about implication. We talked about the implication, for example, P implies Q. We talked about if and only if, and now there is no good way at this point. There is no good way to basically categorize all of these things into good categories. But that's basically how it goes. There is no way to do that at this point, because we don't really know the whole thing yet. So we have to do it step by step. So now the next thing that we want to do, we want to basically find out how we can basically validate these statements. Meaning that if you have some statement, whether that includes the negation, if then, contrapositive, converse, using connectives, using quantifiers, some statement in this form, some statement in this form, P, if and only if and only if Q, for example. So if you basically have some statement, do some sort of operation on it, then you want to basically know how you can validate those, how you can validate that statement, meaning that decide whether that statement is true or false. Is true or false. So that's basically what we want to do in this section. So basically it says that in this section we will discuss when a statement is true. To answer this question, one must answer all the following questions. So to answer whether a statement is true, you have to answer these following questions. First, you need to know, what does the statement mean? What would it mean to say that this statement is true and when this statement is not true? So what does this statement mean? What would it mean to say that this statement is true and when this statement is basically not true? Now, the answer to these questions depend upon which of the special words and phrases and which of the implications, if and if and only, and if then and which of the quantifiers for there exists appear in the given statement. Of course, depending on which one of these you have used, of course, then the rules are going to change. So here we shall discuss some techniques to find the statement, to find when a statement is valid. We shall list some general rules for checking whether a statement is true or not. So there are some rules over here, and they've been enumerated as rule number 1, rule number 2, rule number 3 here, rule number 4, rule number, and there are 4 rules. And then that you can do also by contradiction, meaning that you can contradict what you want to, basically, you can contradict your statement. Now then you can basically probably decide whether the contradiction is true or not. And then based on that you can decide whether the original statement was true or not. And that is also one thing. And then we have some exercises and then some miscellaneous examples. So there is not much here to discuss. But let's go through the 4 rules. So rule number 1 is if P and Q are mathematical statements, then in order to show that the statement P and Q is true, the following steps are followed. So it's very simple. For example, when you have and or when you have or and so on and so forth. Okay, so rule number 1. Rule number 1 is if P and Q are mathematical statements, if P and Q are mathematical statements, then in order to show that the statement P and Q is true, statement P and Q is true, the following steps are followed. So basically what we have here is that we have P and Q as mathematical statements, and basically what a mathematical statement is. We have already talked about a mathematical statement. A mathematical statement is basically a sentence which has basically no ambiguity, meaning that you can decide whether that sentence is true or false. If you can decide that, then it becomes a mathematical statement. Now, in order to show that the statement P and Q, meaning that P and Q, as opposed to, for example, P or Q. So in order to show that the statement P and Q is true, now you have to follow these steps. And the steps are basically step number 1. Step number 1 is show that the statement P is true. show that statement P is true. And step number two, show that statement Q is true. So if you can show that basically the statement P is true, and also show that the statement Q is true, of course the statement P and Q is going to be true, because that was basically the condition for the connective AND. We said that AND basically means that the connective, of course, connects basically two statements. And then for that statement statement basically comprising of the first statement and the second statement, for that statement to be true, of course the first statement has to be true and the second statement has to be true as well, as opposed to OR. So in the case of OR, for example, we said that if you have one first statement here, one second statement here, and you have this connective over here, so then in order for the whole statement to be true, basically either this statement is true or this statement is true, or both of them can be true. So that is the condition for OR. So that's basically why they have introduced these two steps here. Now rule number two is regarding the statements with OR. Regarding the statements with OR. So now again, if P and Q are mathematical statements, then in order to show that the statement P or Q is true, you need to consider the following cases. So case number one, by assuming that P is false, show that Q must be true. Assuming that P is false, show that P is true. And case number two, by assuming that Q is false, show that P is true. This is actually Q. Assuming that P is false, you show that Q is true, or by assuming that Q is false, you show that P basically must be true. They have the kind of language that they have used is show that P must be true. And I suppose what they mean by must be is, well, the same thing as is, I suppose. Unless they mean something else specifically with the phrase must be that I'm not aware of. Otherwise, at this point, I can safely assume that must be here means is. And this assumption has not been proven wrong, never in the past. So I've had no problem with this. I've had basically in the past, I've had no problem with this assumption. And that's the kind of thing that you, most of the time, that you need to do when you're learning something new. For example, suppose that you're learning physics, you're learning chemistry, you're learning mathematics, and I don't know, you're learning electronics. Since the books that you read, of course, nothing is perfect. Everything has their own flaws, and logic has its own flaws as well. So even if the books that you used were completely perfect, then there would come in the inherent problems and imperfections with logic, and so you could not write any perfect book because of the inherent problem with logic. So then, while you're learning something new, you have to basically make assumptions. And for example, over here, the word, for example, must be, or the phrase must be, has never been defined in these old series of books. And you have to make some assumption and assume that, for example, it means either this or that. So now I have made the assumption that must be, what they mean by this is the word is, and this assumption has not been proved wrong in the past. So now there is another rule over here, which is rule number 3, which is rule number 3, which is statements with if-then. Statements with if-then. So in the case of these statements with if-then, what you need to do in order to prove the statement if P then Q, we need to show that any one of the following case is true. So you want to prove that, basically, in order to prove if P then Q, then you need to show that any one of the following cases is true. So you need to show that any one of these cases is true. So case number 1, by assuming that P is true, prove that Q must be true. Prove that Q must be true, which it has been called basically the direct method here. That has been called the direct method. Now case number 2, by assuming that Q is false, prove that P must be false. Prove that P must be must be false, and that is basically the contrapositive method. That is basically the contrapositive. That is the contrapositive method. So basically, in the case of these if-then statements, we said that if you have P implies Q, meaning that if you have if P then Q, meaning that if you have if P then Q, then what that means is that we said that in the case of these statements, you have basically this. I repeat this again because I need to repeat it, since I need to repeat this until I have learned this properly. Otherwise, I know that I'm repeating this. Okay, so before moving any further, I would like to repeat the if-then part one more time, because it's important, and well, that's basically why I always emphasize the importance of not learning something not learning something wrong. There are basically two different things. First of all, these two things are absolutely prohibited, and you would get into trouble if you do so. Number one, do not learn anything. Do not learn anything wrong. For example, I was talking to someone a few days ago, and he thought that, for example, the absolute value of 0 does not exist. Okay? So when I asked him, for example, what is now the absolute value of that, we were actually solving some problem, and I asked him what is the absolute value of 0, and he was perplexed, he was confused, he didn't know even what to say, because he thought I wasn't even supposed to ask the question, because it doesn't make any sense. It didn't make any sense to him. For example, the absolute value of 2, it is equal to 2, the absolute value of negative 2 is equal to 2, but since 0 is neither positive nor negative, it makes no sense to write the absolute value of 0. It makes no sense. It made no sense to him, of course. So when you learn this kind of thing, it messes with your mind, basically with your system of understanding, and it's usually very hard to get rid of it. Especially when it sits very deep inside your mind. Number 2, do not make any wrong assumptions. Do not make any wrong assumptions based on what you read. So, for example, in physics, we read, for example, V is equal to IR. So what that means is that V is equal to IR, of course. That is absolutely correct. But it does. But when you say V is equal to IR, this statement does not mean that V is only equal to IR, and anything else that you write about V would be wrong. Of course, V could be equal to IR, it could be equal to, I don't know, for example, dq by dt, it could be equal to any other thing that happens to exist in the framework of physics or electronics. Of course, dq by dt I gave you just as an example. I'm not really sure if that's actually correct. But, for example, when you read, for example, P implies Q, this does not only mean that if P is true, then Q is going to be true. It could have, basically what I just said could of course be true, and in fact that is true, but it could have many other sorts of implications and many other sorts of meanings. That, I mean, there could actually exist many other ways of understanding this statement. And then when you make this assumption that basically P implies Q means only that, then it's going to be hard to accept that P implies Q could also mean this, and also that, and also that, and so on and so forth. So do not make any assumptions based on what you read. What you read is, of course, if it's correct, it's correct. But it doesn't mean that other things are not correct, or other things could not exist regarding that topic, or that basically that topic that you read. Okay? Now, so this is the problem that I have personally had since the time I went to school, and this has created so many problems for me. Of course, I'm taking care of the problems one by one, but some of them stick in your mind, especially if they are deep. They have basically they have been sitting deep in your mind, so you don't want to create troubles for yourself. Okay. Now, about P implies Q, and I have repeated this probably four times already in this series of videos. About P implies Q. So what we have is that. So about P implies Q, which we can also basically we can also talk about this as if P then Q. So what we can say is that, first of all, P implies Q is, well, P implies Q, and the notation for that is this. Now this says that if I assume that here P is, for example, is a statement, a number is divisible by 9, and Q is another statement, a number is divisible by 3. So when I say P implies Q, or if P then Q, what that means is that if a number is divisible by 9, then that number is divisible by 3. Okay? Now, there are 4 different ways that you can understand this, right? So the first thing that you can say about this is that P is a sufficient condition for Q. The first one is P is a sufficient condition for Q. P is a sufficient condition for Q. Meaning that knowing that a number as a multiple, knowing that a number is a multiple of 9 is sufficient to conclude that the number is a multiple of 3. Now this part I don't really, let's see. Number 2 is P only if Q. P only if Q. And I think my problem is in this part. Let me take care of this. Okay, so I did read a couple of things about these statements, and as it turns out, it's much more complicated than this. And basically, what we read over here is just a very teeny tiny part of the whole thing. So you cannot really expect to understand anything logically based on what's being presented here. I hope that the whole thing basically comes together somehow logically in the book in the next book that we have. Otherwise, if you have any sort of confusion or problems here, that is actually normal, because it's been being presented. It's been being presented in parts and pieces, and not the whole thing has been presented, so there is no logical way really to understand the whole thing, and that might create confusions in it. Actually, that has created confusions in me. But anyway, what we were doing here, meaning that all of these if, then, and if and only if, and all of these things have actually, they have truth tables and everything logical. So you have to basically go based on the truth table to know what is false, what is true, and so on and so forth. But the truth tables have not been given here. There is a bunch of sentences, and it's not easy to find your way through the material through sentence, because a sentence you can make sense of a sentence in many different ways. But the truth table is something that you can see and understand, and there is no confusion and ambiguity there. For whatever reason, the truth table has not been given here. So that's basically the thing. Otherwise, it's really no problem. I think the problem will be taken care of as we go along. So basically what we have here, we said that if we have P implies Q, then very simply, and to put it in simple terms, number one, it means that, well, P implies Q, and I have not written that as number one. Number two is P is sufficient condition for Q, meaning that, for example, in this example, you can say that if a number is divisible by 9, it's sufficient condition for the number to be divisible by 3, right? Meaning that if you know that the number is divisible by 9, then you can basically this reason, or this this piece of information that you have is sufficient to conclude that the number is divisible by 3, okay? And then number 2 is P only if Q, which means that this says that basically a number is a multiple of 9 only if it's a multiple of 3. So that makes sense as well, meaning that here we say P implies Q, and Q is basically the number is a multiple of 3, and P is, well, surprisingly it does make sense, meaning that here we are saying, in Q we are saying that the number is a multiple of 3. In P what we are saying is that the number is a multiple of 9. And P only if Q, what that means is that the number can be a multiple of 9 only if it's a multiple of 3. So that way it does make sense as well. And that's basically the meaning of P only if Q. And of course I could basically, you could search the internet and find a couple of basically articles about these if, then, and if and only if, and so on and so forth, the truth tables and everything. But I don't want to mix it up. If I mix it up, I will definitely mess it up. So I don't want to do that, because we are basically progressing based on this system. And of course, I know that eventually this system will take care of itself. If it doesn't, then we will integrate some part of a book, or a book that will take care of everything from the very beginning to the very end in a very logical manner. So, and then number 3, you can say that basically Q is a necessary condition for P. Q is a necessary condition for P. Meaning that when a number is a multiple of 9, then it necessarily has to be a multiple of 3, which is basically what we said over here. So we can actually forget about this. I suppose we can forget about this one, meaning that this is the same thing. P only if Q, meaning that only if Q is basically only if a number is a multiple of 3, then it can be a multiple of 9. So that means that Q is a necessary condition for P. It's basically the same thing. And also, not Q implies not P. Not Q implies not P, meaning number 3, not Q. That's actually part of the truth table. Not Q. Not Q implies not P. Not P, meaning that if you have P then Q, then not Q implies not P, meaning that if Q is, or the negation of Q implies the negation of P, meaning that if a number is not a multiple of 9, if a number is not a multiple of 3, then it's not a multiple of 9. Okay, now I don't really remember what we were actually doing here. We were talking about these rules and cases and so on and so forth. Okay, so we said that rule number 3 was basically this thing over here. So to sum this up, when you have P then Q, there is only basically, well, this is not a part of understanding P then Q. That's just not Q implies not P. Okay, so that's not a part of understanding P then Q. There is only 2 things that you need to understand for now about P then Q, which is P is a sufficient condition for Q, and Q is a necessary condition for P. So P is a sufficient condition for Q, and Q is a necessary condition for P, and we gave 2 examples here. So that we already understand. So let me write this down before we move any further. Okay, so we were talking about rule number 3, which is statements with if-then. And that is basically in order to prove if P then Q, show that any one of the following cases is true. So by assuming that P is true, so if P is true, then prove that Q must be true, which is called the direct method. And by assuming that Q is false, prove that P must be false, and that is called the contrapositive method. Now, why that is, you don't want to get into the reason because you would get lost, okay? And the reason why I'm saying this is that basically they have not supplied us with the whole logic, so you cannot, and therefore you cannot basically look for the reason. It's just you have to just take it as it is for now, and then later everything will take care of itself, hopefully. If not, we will take care of the problem. But for now, if assuming that P is true, you have to prove that Q is true, which is called the direct method. And if basically assuming that Q is false, then you have to prove that P is false, and that's called the contrapositive method. Now there is another rule over here, which is rule number 4, which is statements with if and only if. Rule number 4, statements with if and only if. So statements with if and only if. So in order to prove the statement P if and only if Q, P if and only if Q, which is also written as P if and only if Q, meaning that P implies Q and Q implies P, we need to show that one, if P is true, then Q is true. So if P is true, then Q is true. And if Q is true, then P is true. Number 2, if Q is true, then P is true. Then P is true. So if and only if, so what you need to do, if P is true, Q is true. If Q is true, P is true. So as an example, check whether the following statement is true or not. So for example, if for example, let's say you have if basically x and y belong to the set of integers are such that x and y are odd, are such that x and y are odd, then xy is odd. Then xy is odd. That is the statement. So the statement that we have is if x and y belong to the set of integers and they are such that x and y are such that basically x and y are odd, then xy is odd. Okay? Now to check the validity of the given statement, we apply case 1 of rule 3. So case 1 of rule 3 was, so this is clearly a case of if-then statements, right? So if-then statements, in the if-then statement we said that basically to prove in order to prove the statement if P then Q, we need to show that any of the following cases is true. Any of the following cases. For example, we said that case 1, by assuming that P is true, then prove that Q must be true. Prove Q must be true, which was basically called the direct method. And case 2, we said that assuming that Q is false, assuming that Q is false, so this is P and this is Q. prove that P must be false. So now if Q is false, now you want to prove that P is false. So that's basically how you, that is basically the contrapositive method. That is called the contrapositive method. That is called the contrapositive method. So what that means, that if I apply case 1 over here, now if I assume that P is true, then I need to prove that Q is true, which is called the direct method. Now my P here is basically assuming that X and Y belong to the set of integers and X and Y are odd. Then I need to prove that XY is odd. And so as the solution, what I need to do is that as the solution, what I need to do, so let P, this statement P, be X comma Y belong to the set of integers such that X and Y are odd. Such that X comma Y, X and Y are odd. X and Y are odd. And Q is XY is odd. So now you want to prove that XY is odd. Now here what we have here is to check the validity of the given statement. We apply case 1 of rule 3, which is basically this thing over here, which we said that now assuming that P is true, assuming that this is true, I want to prove that this is true. And that is assume that if P is true, meaning that if P is true, then Q is true, right? Now, P is true means that X and Y are odd integers. P is true means that X and Y are odd integers. And then X is equal to, then if basically P is true, means X and Y are odd integers. Therefore, so then what you can write about X and Y is that basically X is equal to 2m plus 1 for some integer m. For some integer m. And Y is equal to 2n plus 1 for some integer, that's not integer but integer n, for example. So I can, since these are odd numbers, I can write them as 2n plus 1 and 2n plus 1. That those two becomes odd numbers, of course. And these are two integers, right? So now I can write x times y is equal to 2n plus 1 times 2n plus 1 times 2n plus 1, which is the same thing as 2m times 2n plus 2m plus 2n plus 1, which I can write as 2 times basically 2 times 2mn plus m plus n plus 1, okay, which is again some odd number. You see 2 times some integer times 1 plus 1. This shows that x plus y is odd. So you can conclude that x times y, it shows that x times y is odd, because again you got it in the same way that we defined, for example, x or y or both of these numbers basically. So that means that the given statement is true. That means that the given statement is true. Okay. Suppose we want to check this by using case 2 of rule 3. We will proceed as follows. So now we want to solve the same problem by using case 2 of rule 3. So let's get some space over here, and then we will try to solve the problem that way as well. Okay, so basically case 2 of rule 3. So the statement that we had was basically if x and y belong to the set of integers such that x and y are odd, then x times y is odd. That's basically we want to show that we want to check whether this statement is true or not. So I can take this as this is if, of course. I can take this as P. I can take this as P, and then I can take this as Q. And so case 2 of rule 3, we said that if you have P implies Q, then you need to show that if not Q, then not P, right? You have to show that by assuming that Q is false. So by assuming that Q is false, prove that basically P is false. Prove that P is false, which is called the contrapositive method. Okay, so now in order to do this, meaning that using case 2 of rule 3, basically meaning that by assuming that Q is false, so proving that P is false, what you can do is we assume that Q is not true. We basically assume that Q is not true, and this implies that we need to consider the negation of the statement Q. So that means that we need to consider the negation of this. When Q is not true, that means that the negation of xy is odd would be xy is even, right? So not q would be basically the product xy. The product xy is even. And this, if this has to be even, this is possible only if either x or y is even. And this shows that p is not true. So then this is possible only if x or y is even. Otherwise it's not possible really. So, and if that's the case, then that means that basically this shows that basically p is not true. P is not true, and so thus we have shown not q implies not p. Not q implies not p, which means that the statement that we started with is actually true, right? So, because the statement is, if you can show that if basically p is true, basically p then q, p implies q, you can do it in two ways. The direct way was basically, the direct way is showing that if p is true, then q is true. That is the direct way. And the contrapositive way is that not q is true, then not p is true, which is the contrapositive way, contrapositive method basically. So if any of these you can show, that means that the statement that you started with, which was basically p then q, or if p then q, then that means that statement is actually true. So yes, the above example illustrates that to prove p then q, it is enough to show not q, then not p, which is the contrapositive of the statement, p then q. Okay, so that's basically that, and then we have a couple more things here to take care of. For example, let's say you have example number 14. You want to check whether the following statement is true or false by proving its contrapositive. And if x, y, so we want to check whether the statement is true by proving its contrapositive. So if you can prove if you have basically, of course, if you have p then q, p implies q. If you prove the contrapositive, that means that you have proved that p then q is true, right? So now the statement that you want to prove is basically if x and y belong to the set of integers, in such a way that xy is odd, think we already did this, right? Check it. X and y are odd, then xy is odd. And here x and y belong to the set of integers such that xy is odd. I see. Okay, so here x and y belong to the set of integers such that xy is odd. Xy is odd. Then both x and y are odd. Then both x and y are odd. So you can have you can put an if over here. That means that you can take this as your P, and then you can take this as your Q, for example. So then you can name your statements as below, meaning that you can say that P is basically xy is odd, and your Q is both x and y are odd. And of course you know that x and y are integers, right? So you want to basically prove this using the contrapositive, and I suppose we will actually do this in the next video. This video is getting too long.